All right, let's go ahead and move on to our next speaker. We're going to go ahead. You know him. Cece loves him. We have our very own Dr. Sharp here today to talk to us about Dr. Impact. So we're very excited for his presentation coming up. And so, Dr. Sharp, whenever you're ready, we'll go ahead and start with your section.
Okay, I'm going to go ahead and share my screen and show you my slides and my stuff. Now, what I'm going to talk about today is a sandbox experiment that I do at EC Day and at Night of the Open Door. But when we have people come, I like to demonstrate how impact craters work. And I had help today from Mara Karagiosian, she's my student, and we did some experiments together the other day. So this is Meteor Crater. Now, if I were to ask you how did Meteor Crater form, you'd say, duh, it formed by a meteor impact. Everyone knows that, except I want to tell people that when I was a little boy, people didn't all know that. And there was a great debate among the scientists about what formed this crater. So some of the scientists, including the USGS folks, said that this was some kind of weird volcano. But there were a few geologists like this man, Eugene Shoemaker, who thought it was an impact. What Shoemaker did is he studied craters formed by big explosions, big bombs, and he compared those craters to this crater, and he did this crater mapping for his PhD. And with the help of him and several other scientists, they proved that this crater is indeed an impact crater. And it's just a great example of an impact crater. And if you get a chance to go there, you should. It's really neat and interesting. So here are the experiments, and you could do these at home if you want to. I have some impactors. So I'm going to call my meteors or my objects impactors. We also call them bolides, but I'm going to basically drop those or shoot those into a sandbox. My sandbox is there, and I put orange sand on the top of my sandbox so it would look kind of like the surface of Mars. Underneath the orange sand is some light blue sand, and that way you can see if we get through the surface and into the bluer sand. So let's go ahead and do some experiments. The first thing I want to show is size. Does size matter? So this is me. I have two wooden balls, a bigger one and a smaller one. I'm going to drop them from the same height, and they hit at the same time and the same speed. Okay, they didn't make very big craters, but they made craters, and you can see the blue sand. They got through the orange sand into the blue sand, and that's the size, 4.7 versus 6.3 centimeters. So the bigger ball made the bigger crater. Okay, let's try another one. Now I have these two tiny metal balls, a little tiny one and a little bigger one. Let's do that one. And you can predict what's going to happen. The big one should make a bigger crater, right? Boom, there it is. Oh, that's a nice crater. Let's have a look. Yeah, this one, the bigger ball made a 6 centimeter crater, and the little one made a little one, 3.8. But you can see that the bigger one got deeper and it dug into the blue sand, right? And it actually tossed blue sand outside of the crater. You can see a little bit of hint of blue on the surface around the crater. We call that the ejecta blanket. So when a crater is formed, it excavates material from below and it shoots it out of the crater to make an ejecta blanket. Let's do another one. Now I've got a really big metal one and a tiny metal one. And we'll do this again. And remember, I'm dropping these from the same height, so they hit the sand at the same velocity, right? The difference is the size. So let's have a look at this one. Actually, let's do something else. Let's look at this in slow-mo. Here it comes. Boom. That's what happens when it hits. It digs into the sand and it shoots it out and it makes that ejecta blanket. And you can see that the sand, it even goes outside of the sandbox a little bit, right? It really does. And so here are the craters, the bigger one, and you can see the blue ejecta outside of the crater. And the little one didn't really get into the blue sand, but this one's quite a bit bigger now at 11.5 centimeters. So bigger impactors make bigger craters. Now, is it really size that's important? Let's try this one. Now I have two balls of the same size. One is wood and one is steel. Which do you think will make the bigger crater? Yeah, I think so too. Let's try it. Here we go. Drop from the same height. Now they go at the same speed too, and they hit at the same time. Let's have a closer look at that one. You can see the ejecta from the metal one. There's really no ejecta from the wooden one. And those are the craters. A much bigger crater from the metal impactor than from the wooden one, even though they're the same diameter, they're the same size. So it's not really size that matters, it's mass. So when we think about size in physics, we have a physical size, which is the diameter of the ball, but we have a mass, which is the amount of material, and that turns out to be the important thing. But there's another important variable, and that is the speed or velocity of the impactor. So here, this is the fun part. I get to use a slingshot, and I haven't used a slingshot since I was a kid, but I'm gonna use a slingshot and try it with this big metal ball, see what happens. Don't try this at home, or if you do, be careful. Here we go. Boom, that was a good one. Now, let's look at that in slow motion, because that's just too good. So here it comes. Boom, a big ejecta blanket. It shoots sand well outside of the sandbox. But look, the ball bounces out and lands nearby. This creates what's known as a secondary crater. So there's the main crater, and it dug into the blue sand, and it shot blue sand all over the place. You can even see blue sand out here on the pavement outside of the sandbox. And there's the secondary crater, because the ball bounced and made yet another crater over here. So velocity makes a big difference. So the higher the velocity, the larger the crater. Now I'm going to try one more experiment here. This is sometimes, we always think about craters coming in, that the meteor comes straight down, but we know that when meteors come into the atmosphere, we've seen pictures of it, they sometimes don't come straight down. So let's try one here. This is about 45 degrees. Oh, look at that. I gotta show that one again. The impactor comes in, it makes that big ejecta blanket, and it shoots it down range. And let's have a look at that one. That's a beautiful crater. It's still pretty round. It doesn't look that much different, but it is a little different. It's not quite round. But the important thing is that the spray, the ejecta, goes in one direction. So when we see an ejecta blanket on Mars or something, and we look at the shape, we can tell whether or not the impactor came straight down or at an angle. Now, there's one more thing I want to demonstrate, and that is relative age. So when we look at a surface of like the moon or of Mars, we can tell which craters are younger and older. Now, this is Mara. She's about to make one. Boom. That was right next to the last one I showed you. And you can see here that this crater partially covers up the other crater. So when we see craters that cover each other a little bit, we can determine which ones are younger and older. So younger craters cover older craters. So what determines crater size? Well, the mass of the impactor is very important. The velocity of the impactor is very important. And really it's the energy that's important. And this is kinetic energy, which is given by this equation. It's 1/2 times the mass times the velocity squared. Because the velocity is squared, it's really important, right? So how did meteor crater form? The crater is 0.74 miles across. It's 560 feet deep. Its rim is elevated by 148 feet. So when you walk around, if you get a chance to walk around the edge, you see the edge is high. The impactor was 160 feet, and it was this. It was a metal meteorite, an iron meteorite called Canyon Diablo. So any questions about meteor crater or impacts? I'll take any questions. Okay.
All right, so we could move on to the next presentation. But however, if you have any questions, please feel free to drop them in the Q&A box. And Dr. Impact and his awesome presentation will definitely catch up with the questions and answer all your questions shortly. So we move on to the next presentation. We are now joined by Professor Jenny Patience and PhD student Justin Harm to talk about searching for planetary systems around other stars. Let's welcome them to the virtual center stage.
Hello, welcome to the our afternoon presentation. So I'm Professor Jenny Patience, and I'm here with one of my PhD students, Justin Hom, and we'll describe to you a bit about the research we're doing and the broader field of searching for planets around nearby stars. The images you see at the bottom of this first slide come from an instrument that we've been using on one of the world's largest telescopes. And what you're seeing is the light emitted by young giant planets that are more massive than Jupiter in our own solar system in the first two images. And then the third image is showing you a ring of dusty debris around a young star that's analogous to some of the dust rings in our own solar system. So in this slide, I thought you might be interested to see examples of some of our students at work. So you see Justin, who will be speaking as part of this presentation on the far left, and then other students as well who've been involved in these projects working at some of the largest telescopes in the world. So for a bit of background for understanding how these solar systems around other stars compare to our own, I thought I would just start with a quick snapshot of our own solar system. And astronomers use units that are tied to the Earth. So we say that the Earth is 1 astronomical unit away from the sun, and that's what you see here. And the 1 under the Earth. And you see that Mercury in our own solar system is what we think of as a scorched world. It takes a few months to go around the sun, and just keep that in mind as we look at some of the other systems. And then you see Jupiter at 5 times the Earth's distance, and then other gas and ice planets outwards at tens of times the distance. And we'll see how that compares to other planets around other stars. And I just wanted a quick note that for any of you who go outside tonight, you will have a spectacular view of Jupiter and Saturn are near the moon. And then Mars is also very visible in the sky. So if you're interested in that, you can see just with your own eye. The planets out to Saturn are visible with your eye. And then beyond that, Uranus was discovered by how you might think planets get discovered by observing with a telescope. And then Neptune was discovered indirectly through orbital motion analysis. And so what I'll show next is how we discover planets around other stars. And you'll see that we use both direct detection, that's what my students and I work with, getting actual images of planets, but also indirect techniques are very important for discovering planets around other stars. And we'll begin with that. All right, so what I'll show next is a movie. And this is a simulation that we've developed with our planetarium system here at ASU. And so hopefully in not too long in the new year, you'll be able to come and see planetarium shows again. But for now, we'll give you this simulation. These are accurate locations of the stars in the sky. And what we're doing now is we're first moving outwards and we're visiting the first star, a normal type star that was discovered to have a planet in orbit about it. And so this star is 51 Peg and it's visible to the eye. And what you should see faintly is you see our simulation of the planet orbiting about the star. But what you notice is that the star itself is also in motion because both objects orbit about what is called their common center of mass. And so that you can think about as a balance point between the two objects. So you see the star is in motion. And so when an astronomer uses a telescope and gets a spectrum of the star, that's what you're seeing below the star, all the colors of the spectrum. As the star is moving, you see that the spectrum, where the locations of the lines, those are shifting. And this is analogous to when a train moves by and you hear the pitch of the sound of the train changing. As the star is moving towards and away from us, we see those lines move, and that's how we indirectly detect that there's a planet orbiting that star. We don't see the planet directly, but we measure its gravitational influence on the host star. As small as it is, it's measurable with very carefully designed instruments on large telescopes. And so that's how the first planet around another star. And this was the subject of a couple years ago, Nobel Prize award. So that to give you a sense of how spectacular this field is in terms of its impact on astronomy. The next approach is to observe the star again. And if you have a very chance alignment where a planet is in orbit about a star, and the orbit of the planet means that from our line of sight from the Earth, the planet happens to pass in front of, between the Earth's view and the host star. So this is the first star that had a planet detected in this method. And so here what you're seeing in this line below the star, that's meant to indicate the brightness of the star. And then you saw the brightness dip as the planet crossed in front of the star. And so by carefully monitoring many, many stars, then there will be a subset of the stars that show this pattern, where there's a regular steady dip in the brightness of the star that corresponds to the orbital period of the planet. And so keeping in mind how Mercury took months to go around the sun, and we think of that as a very hot planet, in these transiting systems, that's what we call the systems where the star goes in front, they're only days in some cases. Now we're moving into imaging, and you see a simulation of a standard image of a star where there's a bright star and it's surrounded by this background light. Now, if you can use instrumentation called adaptive optics, that will focus the light of the star. And then another specialized component of astronomical imaging can be to add a coronagraph, which blocks that central brightest part of the star. And now you see faint points of light that were previously invisible. And this is a simulation of planets around a star. And now we're going to show you a simulation of an actual detection through this method of a star that had rings of dust. So that's what you're seeing now. These two rings of dust were known indirectly about the host star. And then in between locations of those dust, we were able to actually image a planet multiple times the mass of Jupiter, it's thought. And now you're seeing the actual astronomical data with their bright point of light is, it may not seem like much, but we were super excited because it's the emission from a young giant Jupiter type planet. So again, we'll just now go back to that simulation, and now we'll zoom out. And what you're seeing now is a field of stars visible from the Earth, and the ones that are circled are known now to have planets around those stars. And at this point, there are thousands of stars nearby that are known to have planets. And what this zoom out is showing is the small region of our galaxy that we've been able to search thus far. And so I hope this is giving you a sense of how even within this small region around the location of our own planetary system, we've been able to discover thousands of exoplanets. These are planets around other stars. And this gives you perhaps a sense of scale of how much more is out there to discover. So next we'll have a movie that Justin will describe the results to you, where we're searching for not only planets, but also those rings of dusty material around nearby stars. So we'll start up this next movie, and Justin will give you details.
Okay, thank you, Jenny. So Jenny mentioned that we're finding these rings of dusty material around other stars, and we have that in our own solar system. That's the Kuiper Belt, icy rocky bodies that their motion is helped determined by some of our own planets. So we've been using large telescopes like the Gemini telescope to look for these dusty rings of material around other stars because they can tell us a bit more about planets in those systems. So we've looked at a bunch of stars, specifically looking for these disks, and we found quite a few. So here are some of the images of them. We see them in a variety of shapes, sizes. They mostly look like rings. This one we're going to next, we're looking at it at a bit of a top-down view. And we've also looked at some systems that we've also found planets around them too, and found evidence that these planets actually affect the shapes and sizes of these rings. So here's an example of one of these systems, the HD 106906 system. The disk is not like a perfect circle, it's kind of ovular, elliptic. So one of the questions we're hoping to answer with this study is, did our own solar system look like some of these dusty ring systems when it finished forming planets?
And we're happy to take any questions. If there are any questions about these results, you're welcome to ask. It's harder for us to see the chat, but I think someone might be able to call them out to us.
So there are questions in chat that can be typed out and answered. We're actually going to move on to our next panel. I'm going to introduce, we actually don't have any presenters, but we do have a video from the Planetary Society at ASU. So we'll get to their presentation, and then any questions that you have regarding the Gemini Planet Imager can be answered in the Q&A section. So let me share that video that the Planetary Society sent us. And there we go.
Hi everyone, my name is Cameron Reed and I am president of Planetary Society at ASU, and I'm here with Andrea and Melanie, and we are a planetary and space science organization here on campus at ASU. And today we're going to be talking about Martian and Earth analogs and how we can better understand the surface of Mars using what we know about Earth.
Okay, to better understand a planet, we first must understand its geology. And so here we're going to talk about craters in two different types. We have impact craters and Mar craters. These images down here below would be those examples. On the left, we have the Barringer crater, which is actually located in Arizona. It's about 37 miles east of Flagstaff. And this is an example of an impact crater. And what that means is that this is an impression of something that has hit the Earth. And so about 50,000 years ago, a meteorite actually hit the Earth to create this and left this for us to see. On the right, we have the El Gigante crater, which is located in the Sonoran Desert, Mexico. It's about 800 feet deep. And as similar as it is to this impact crater, it was actually created from a volcanic explosion. Okay. On this next slide, we have another impact crater, but this is actually an image that was taken from a thermal emission imaging system operated by ASU. And this image is from a crater on Mars. And so two things to really look here. We have this squiggly line around this little bulbous area. The squiggly line is an ejecta ring. And so we know this is an impact crater because of this ejecta ring. It's formed from explosive material that's actually injected from an impact that you can visibly see. And the center here is what we would call rebounding. So on that impact, the force has superheated the rock or the surface into a liquid form that then rebounds to the center. That creates this bulbous area.
Some of the most important and defining features that we can find on both planets, Earth and Mars, are valleys and channels that have been carved by erosion and water. And water is a huge thing that we always look for on other planets, and helps us understand the planet's history by looking at these valleys. So this is an image of part of southern Utah, and this Canyonlands landscape is a pre-defining part of Southwest. And it's also a good analog to the arid landscape of Mars and any time that there may have been water on Mars. They carve valleys. So we don't have anyone on Mars in person to look at these. We do have imaging, and this is an image of the surface of Mars. And in this image, you can see a lot of different features. This is a good image to display that. And you can see a lot of valleys that have been created by possibly water at one point, these dry riverbeds perhaps. Lots of craters, there's different sizes of craters, and they have defining features in them. Some of them are a little bit more raised, and others are a little bit flat and less well-defined. So different ages perhaps. And a lot of these craters are actually on top of these dry riverbeds. So that tells you that these craters are younger than the riverbeds upon which they lay. So there's been enough time for lots of craters to accumulate on the surface of Mars since there was last flowing water in this part of the planet.
Another geological feature we will discuss are canyons. We study canyons to gain an understanding of how our planet's geology stands against the elements of our earthly environmental processes. A very popular canyon and close to our homes here in Arizona is the Grand Canyon. Now, the Grand Canyon is devastatingly beautiful to look at. There's no doubt about it. But there's much more to this canyon that makes it scientifically interesting than just its beauty. And to us, that would be the way in which it's formed. And we know that this canyon was formed by water erosion, or the cutting away of rock material over time by water. And so this means that over millions of years, water bodies, or as we know it today to be the Colorado River, has cut away to expose the many layers of rock that we're able to see from standing at the side of the rim at the canyon. And then, you know, there are other ways that canyons are formed over time, and that could be through erosion by wind or tectonic movement. And we'll look at an example of a canyon formed by tectonic movement in a moment. But what's really important to understand is that we're able to take this knowledge of how canyon features are formed on Earth and apply it to features that we see on other planetary bodies, so that we're able to come to a conclusion on how these features were formed there. And so the example that we're going to look at is a canyon very, very far away from our homes here in Arizona called Valles Marineris. And so this canyon is not located here on Earth, but could be found instead cutting across the surface of Mars. And if you thought that the Grand Canyon was big, Valles Marineris could swallow the Grand Canyon up in size over and over again, being that it's 4,000 kilometers long. And just to give you an understanding of what that means in length, and I know that we said that the canyon is not located on Earth, but it's been superimposed here on a picture of the United States just to show that almost like 4,000 kilometers in length looks like a distance between coast to coast in the United States. So from California to New York, which is pretty big. And so similarly to how Melanie and Cameron before explained that we could use photos shown to us on craters and valleys, we can do the same with this canyon. So if we want to gain an understanding of how this canyon is formed, we can look at aerial photos to do like a visual survey of the features so that we can study how it was formed. So as you can see here, the linearity of the main segments of this canyon indicates to us that it was formed through tectonic movement. And so this means that as the planet cooled, there was movement beneath the layers of the surface that caused this giant fissure or crack to break away the layers of the Mars surface. And so even though what we're looking at face value, without understanding some of the processes that we've explained by looking at these features, it just looks like a riverbed, like water could have just come through and eroded away these layers. But because we are able to apply other methods of study to these features, we can gather these clues to tell us more about what actually happened here.
Now, just to close this out, I highly recommend that you all go and visit the Themis website, and you can see all these live images from Mars, and they're also sorted by what images contain. So it's a great resource to look at and learn more about the surface of Mars. And also keep updated on Mars 2020 mission, which ASU is part of for the camera system on it. There's all these great missions that ASU is part of here. And if you have any questions or you want to learn more about TPS at ASU, feel free to contact me or the club, and follow us on social at ASU Planetary Society on Instagram. Thank you.
All right, thank you to the Planetary Society for that wonderful video. Up next, we have a sneak peek into astronomy in different cultures. Our presenter will tell us more about CC Multicultural Milky Way. Let's have her take the center stage.
All right, hello everyone. And you should be able to see my screen now. So my name is Dr. Karen Neerman, and I'll be talking to you today about the multicultural Milky Way. This is work that I've done to compile these stories through the Astronomy and Astrophysics Postdoctoral Fellowship. And so a thank you to the National Science Foundation for that. So why is our galaxy called the Milky Way? And we're going to have a poll up here for you guys. So when we look up at the night sky and we see that cloudy band, is it a candy bar? Is it mother's milk? Or is it melted ice cream? So. And then also, which regional version would you like to hear about first? Excellent. So you can take both of those polls right now. And so our Milky Way is, we see that as that band of light, and that's because our Milky Way is shaped like a Frisbee. And so we are inside that Frisbee. And so the most of the stars in the Milky Way are then along that band. But all the other stars in the sky are also all part of our Milky Way galaxy. So, all right, we'll give it a couple more seconds for everyone to vote. And I see most of the people, so we can end the poll right there. So most of the people have chosen right mother's milk. Excellent. So the Greek mythology is that that is the milk from Hera, the goddess. And so since this is a choose your own adventure talk, we're going to head off to northern Arizona and learn about the Navajo culture. And so the Navajo people, they only tell their sky stories during the winter. This here is a picture of the Milky Way over Monument Valley. And so they call the Milky Way that which awaits the dawn, or Yakaizdaha. And it is the corn's pollen that is sprinkled before morning prayers. This image here is a depiction of what that might look like in a Navajo sand painting. Another story about it is that the stars were being gently placed as quartz shards up into the night sky, and Coyote, that trickster, got very impatient and took the blanket and threw it up, and so those quartz shards and the dust from the quartz that were left then formed that Milky Way band across the sky. So if we go back here, I think second place in the poll was Southern Africa. So this is the San people, or the Ham dialect, and they of course can see, they don't see the same Milky Way that we see. They see the Southern Milky Way, which has a lot more of this dust and gas, and it's a lot more exciting. If you ever get to go, I encourage you to find a dark place to look. And their story, this is a quilt made by the first people artists of the Bethesda Art Center, and these are the artisans that worked on this quilt. And this is about the girl who made the stars, and she was separated from her village, and then was very upset about being separated from the village. And so in her anxiety and her frustration, she took the blanket next to the campfire and threw it up, and the ashes from that campfire then became the Milky Way that we see today. And that is a path for people at night to follow, to find their way back to their villages. And let's go to one more, and I will, let's go to the southern Mexico. And so southern Mexico are the Maya people. We often think of them as being more of a ancient people, but the Maya people are still a vibrant culture. And so I'll tell two stories. So one of those is about the celestial dragon here. And so they call the Milky Way, this is the glyph from one of the temples there. And so this is the celestial dragon. And so it has two heads, here and here. And also on its back are glyphs indicating various celestial bodies like the planet Venus, which was very important to the Maya. And the modern Quiche Maya, they look at two different parts of the Milky Way, the one that is more solid white, they call the Saki Bay. And then the part of the Milky Way that has dark, like these dark dust lanes here, that is the underworld road. And in the constellation of Cygnus the Swan, there's this big, dark, great rift, we call it, and that is actually the door to the underworld. And we have one more that I'll go over very quickly. This is in China. The Milky Way is called the Silver River. And this picture here is the Summer Triangle. So Vega, Deneb, and Altair. And Vega is the weaving maid, and Altair is the cowherd. And they fell in love, and the weaving maid neglected her celestial weaving duties and came to Earth, and they raised two children. But her parents got very upset, and so they came back and they took her back up to her celestial home. And the two of them pined very hard, and they were then allowed to meet once a year on to able to cross the bridge of the Milky Way, the Silver River, on a bridge of magpies, and that is celebrated in the 7th month, on the 7th day of the 7th month. 2 years ago, that happened to be toward the end of July. They use a lunar calendar. And so it's still a celebration today, often kind of has some elements of our like Valentine's Day celebrations. And if there's time, I can take some questions. Otherwise, here's a drawing of the two of them. Otherwise, thank you very much. And may you have clear and dark skies so you can see your Milky Way.
Thank you so much, Dr. Neerman. If you guys have any questions for Dr. Neerman, you can go ahead and leave them in the chat and we'll make sure to monitor those. But our next presentation is brought to you by a couple of people. It's gonna be a little bit of a group effort here, but we're gonna talk about Psyche. And so Psyche is the name of a mission, and it's the name of an asteroid, and it's also the name of that mission to go and visit that asteroid. So our very own Dr. Lindy Elkins-Tanton wrote a proposal to go and visit Psyche the asteroid, and ASU won. And so now we're in charge of this mission. And so what we're excited to do is build a spacecraft. It will not be crewed, unfortunately, so it's going to be instruments only. But we're going to send it to Psyche. So it launches in 2022 to land, or not necessarily land, but to arrive at Psyche in 2026. And the reason we're so excited about this is, one, it's an asteroid the size of Massachusetts, so it's incredibly large. And two, it's in our asteroid belt. So it's between Mars and Jupiter, or in the outer parts of our asteroid belt. And so we're really excited to visit this asteroid and what we believe is a planetary core, or the leftover remnants of a planetary core. And this is the first time that humans will be able to explore a planetary core in the history of space travel. So we're very excited to be a part of this mission and leading it. And so what we're gonna do now is I'm gonna go ahead and share my screen, and we're gonna watch a quick little video that explains Psyche.
Alicia, you might have to reshare. We're not getting any sound.
Sorry, Alex, did you say we're not getting any sound?
Yeah, we don't have any sound on our end.
All right, let's try this again. 1 second. All right.
My main interest in planetary science is because it's the closest part of the cosmos that we can actually go, see, visit, and probe. Psyche is a larger asteroid in the main belt that is in between Mars and Jupiter. Our experience so far in terms of exploring the solar system has been with either rocky or icy bodies. What's particularly interesting about Psyche is we think it's a metallic object. We have a common understanding perhaps of how regular common rocks behave, but metal behave in a very different way. What I contribute to the mission is trying to understand how cratering and the process of collision and interaction work for a metallic object. And we will use this information then to understand what we see at the surface once we get there. What we did is take an iron meteorite, put it in the chamber and use it as a target for our input experiment. And we were shooting a quartz bead at a high speed in order to produce a crater. Everything has been filmed with high-speed cameras, so we have a tremendous amount of data that shows in high resolution what happened during the contact, during the explosion, and how the crater forms on the surface. So everything has been documented in great details. Here we have a piece of the Gibeon meteorite, and what we see here is a crater that was produced as a result of one of our experiments. And traditionally with rocks, the rim would be blasted away and would be a sort of flattish feature. But here we see these flaps that basically are frozen into place. And this is because the metal is much harder than rocks. And so you can then retain this interesting morphology. There's going to be a very exciting phase of the mission when we actually start gathering data. And there's going to be lots of surprises. I just can't wait to be there and see whether or not there is, any resemblance with this model or not.
Meg, it looks like your volume's off in the corner.
So next to the pause button on the video, there's a little volume icon, and that looks to be muted.
Understanding these rocks and the places they come from. When I was a little kid, I thought I wanted to be an astronomer. And I took a geology class, and there was just something about having a rock in your hand, something you could hold and feel. I thought, we have rocks from outer space. Maybe I'll study those. I study meteorites. I love meteorites. It's like an addiction for me because I love exploring the solar system through understanding these rocks and the places they come from. Life on Earth exists on two heat engines. One is the sun, but the other is the heat engine below our feet that drives the movement of the plates. It drove the differentiation of the planet. We've known for 2 centuries that our core was made of metal, but we haven't been able to explore it. We can't drill a hole that deep. We can't explore with any kind of submersible in the oceans. What we've been looking for years is a metallic asteroid, something that's very dense. Psyche is an asteroid 200 kilometers across, thought to be metal rich. Psyche is our way to explore our own planet. We have meteorites fall to Earth. Some of them are little tiny pieces. Some of them are the size of cars. But compared to Psyche, they're just tiny little specks of dust. When I first started as a graduate student, we had never visited an asteroid, not any of them. Asteroids were points of light in the sky, and now they're real geologic places. They're places we can visit. More than the awe, more than the wonder, So we have this responsibility to do this right. And that's why this part is so important, what we're doing right now, designing these instruments, because that will determine whether we get the data that graduate students 10 years, 20 years, 30 years from now will learn things about this asteroid that we can't even imagine today. It's the journey of a lifetime, and I didn't want to miss it.
Psyche is a unique object in the solar system.
To us, Psyche is this
Oh, we just lost sound for the video.
Kim, looks like you're gonna have to unmute your mic.
There we go. Perfect.
Psyche is a unique object in the solar system.
To us, Psyche is this really unusual body giving off really unusual gamma ray neutron signatures.
Technically, it's an M-class asteroid out between Mars and Jupiter.
One of the first things you want to know is what's it made of.
So the Psyche payload consists of 3 science instruments. One of them is what's called a gamma ray neutron spectrometer. It's actually 2 separate pieces of hardware. One is the gamma ray spectrometer and the other one is the neutron spectrometer. Both combined study the elemental composition of Psyche.
If you know the surface composition, what it's made of in terms of iron and nickel and silicon and oxygen, you can then start to say something about its history and how it formed and how it evolved.
By using gamma ray spectroscopy, we can measure those elements remotely. We don't have to touch the surface. We don't have to dig into the surface.
For Psyche, we're building kind of what we call the Cadillac. It's a very high precision, high sensitivity instrument. It's very similar to the MESSENGER instrument.
That technology that we developed for the MESSENGER spacecraft gave us a huge head start going to Psyche.
For our types of instruments, we don't get to fly them very often. So when we actually get selected for something, that's a big deal for us, where we can, take what we learned from the prior missions and implement it now and make an even better instrument.
Our instrument is kind of like a camera without a telephoto lens.
In order to get our best measurements, we need to be relatively close altitude above the surface. That's what we call orbit D.
So we can form maps, global maps, of the elemental composition of Psyche just by flying around externally.
You have galactic cosmic rays. That's a fancy word for very fast protons. They come in, they smack a planetary surface, they bust apart the atoms in that surface, all the neutrons rattle around, and as they rattle around, they end up producing gamma rays and neutrons that come out. And the gamma rays have energies, and they're like a fingerprint. So if you get the fingerprint of different energies, it says, is iron there, is nickel there, is silicon, and then how many of those gamma rays tells you how much of that element is there.
The first thing it takes to do a mission like this is a tremendous amount of institutional knowledge of all the different aspects, not just how do you build something, how do you aim something, how do you guide something, how do you get data from something, those technical aspects.
I feel like it's super important to have a team that you can trust, because you can guarantee that at some point something's going to go wrong, probably many things over the many years of a project. So already it's happened that in my process of learning about the science, I've made small changes to the design to help optimize and help meet the science goals.
We're kind of the last instrument to get its measurements.
And so there is a sense where you're on pins and needles until you get that data back, and then there's a big relief, there's big excitement, and then you get to work and trying to say, what does all this mean?
So we'll deliver some excellent science at the end.
Very exciting video from the Psyche team. All of us at ASU are very excited to be part of such a really significant mission. Our final panel and presenter, last but certainly not least, is astronaut Katie Coleman. Here at ASU, she's our ASU Global Explorer in Residence at the School of Earth and Space Exploration and the Planetary Initiative, and she has a great presentation for you guys. So, Katie Coleman, you are up in the stage.
Well, hi there. Can you hear me?
Yep.
Okay, great. Sticking my mic in the right place. Sorry about that. Well, hello, everyone. I was just having the best time learning about Psyche. And there's something so special about learning about it from the people who are really doing the work. And I don't know, you could see how much they love it. And it meant a lot to me to do that. I'm interested to go back and listen to more. I love those videos a lot and the people. Okay, so my plan is to show you about 5 minutes of slides and pictures or videos, and then take your questions if everybody thinks that that is practical. So I'm going to go ahead and share my screen here. And let's see. I'm going to do this. You'll get to see my messy screen. I'm going to check these boxes. My videos do not have sound, so we don't have to worry. I am the sound. And let's go right here. And does everybody see a big white spacesuit and a sort of tiny Katie head there? I'm going to pretend you're nodding.
Yep.
Okay.
Good.
Okay, so that's a picture I'm actually really proud of, because you only get to have your picture taken in the big white spacesuit if you have qualified to be part of that team. And I am somebody that did that. I'm the smallest person actually to do that for the space station. And I was going to just briefly say I am a veteran of 2 space shuttle missions. The first one was a laboratory mission to figure out, how are we going to do experiments up on that space station anyway? And what can astronauts do? What can scientists do? And how can we make that science happen between space and the ground? And my second one was with this crew here, very famous because of the woman in the middle, Eileen Collins, first woman commander, and famous for the spacecraft you cannot see in the background. It is inside the payload bay of the shuttle. It was the largest and the biggest, the heaviest thing that we've ever brought to space, and that is the Chandra X-ray Observatory. Literally the observatory that, well, it looks at X-rays, that part of the spectrum, the exciting things like stars exploding, those are supernovas, galaxies colliding, black holes sucking things in, spewing things out. Those are X-rays, and there's a lot of really cool X-ray and Chandra-based research. Chandra is the name of the telescope. Chandra-based research that happens at ASU that I'm always proud and happy to be hearing about. It was only supposed to work for 5 years, and it's still working. And this is 21 years later, just about this time of year. And then mostly I want to tell you about life on the space station. And I really loved living there. You can tell that we're not really so far away, not as far away by any means as most of the objects that you've been hearing about. But that's a picture of the space shuttle and the space station together. Here it is from a different kind of view. Some people are thinking, I'd like to go to space. Some people no. The people who say no, often it's because they think it's really tiny and cramped and terrible. It's really not. It's huge and wonderful and amazing. We don't live sort of goalpost to goalpost. We live in the part along the 50-yard line. It's about 10 modules, about the size of school buses without the seats. And usually we go up in groups of 3 or 4. In this case, I went up with the Russians. This is myself, Dmitry Kondratyev from Russia, and Paolo Nespoli from Italy. And here's about a 2-minute video that shows what it was like for us to go. We're actually saluting, checking in. They give us actually literally a little kick in the butt to get up those stairs there. We are inside that rocket. Our little capsule is kind of like cocooned inside a tin can there. And then that is me in the capsule. And here is us in our little Soyuz capsule. It's actually sort of a 3-part spacecraft. And that is my favorite scene of flying through the space station, getting to do robotics and all sorts of different experiments to understand space station science, microgravity science, but also how do we explore further? And what does that mean for us as people? So we can't help but be people. So we all bring a few things up to space. And there's the space station again, and the view out the window. And what's really wonderful now is that, I mean, you can actually watch this all day long because it's on the internet. You can watch yourselves on the Earth. You can see things like Aurora Australis, which doesn't happen. The Northern Lights or the Southern Lights don't happen every day, probably about 6 times while I was there. And here's the Earth at night. And so this is something that you yourself can see on the internet, in books, in films. And I'm just so happy about that because I think it's a view that is really, it belongs to all of us. I used to think that space was someplace else. And now I realize that space is actually very, very close. And it's really just a part of Earth. It's just not enough people have been there. So let me just check and see, do we have some questions? I see a couple questions. And why don't I go ahead and take those questions if that works? And I can show some more slides depending on what the questions are, or if we've got some more, I will do those too. And I'm going to depend on our moderator to tell me when time is done.
Yes. So I know one of the first questions is, what is the lower age limit on becoming an astronaut?
You know, I don't think there's anything, you'll have to check the web, but I don't think there's anything that says what's too young or too old. There is a matter of getting the qualifications, which are, you know, basically having I think a master's level degree in a technical field, so it's going to take you a certain number of years to acquire that. There's no upper age limit, which I'm pretty excited about. John Glenn was, I think, 75, 77 when he went. But, you know, people explore space, and actually in real life, what we need is people of all ages. I mean, I know that I work with a lot of young people and I love being part of ASU. And part of that is because young people didn't grow up with the same ideas of, oh, we can only do it this way that we did. And so they think of more possibilities. So having several generations going to space together, that's really going to lead us further. What's next?
So a lot of people are asking why in some of the videos and pictures there weren't any stars that you could see out in space.
That's just a limit of the cameras and the photographic situation, really. In order for us to really have our best view out the window, it actually takes a little preparation of, you know, they never want us to get lost or not know like what happens when you hit that button, right? And so the buttons are lit, there's writing that lights up on, there's lights everywhere. And a lot of times we literally make a cocoon. Like I used to take extra large t-shirts, dark ones, and then literally put them over my head so that I could then put that on the window and look out the window and see just dark. And it's kind of the same frustration you have when you try to take a picture of the night sky with just a camera. It often, unless you adjust the time and things like that, you just don't collect enough light to see them, but we do see them with our eyes.
Awesome. Another question that we have is, do you have any health effects from being in space so many times?
We're still finding that out, in that I get a physical every year from NASA, courtesy of your tax dollars. Things that we're looking for, but then we're also trying to take a lot of measurements in case, and there's a lot of samples that are frozen and kept. And I mean, I'm part of hundreds of medical experiments, but we certainly look at bone loss. I myself, because it's something that happens to us very quickly up in space, that's kind of the bad news, but it's also the good news because it makes it easier to study. And so I actually came back with the same amount of bone that I left Earth with. And that's what you see when you take literally a bone scan or an x-ray. But probably if my bone is like a pipe, which it is, we've sort of lost bone out of the meaty middle, and it's rebuilt itself through exercise, weight-bearing exercise and vitamin D and things like that on the space station, rebuilt that hard layer on the outside. So our pipes are thicker, but less connected in the middle. We'll see, what does that mean structurally? Are more of us going to have broken hips? So we're doing that research so that when you go to Mars, it's going to be safer for you.
And kind of piggybacking off this, we have a question that asks, how does microgravity affect the psychological aspect of the astronaut's health? So how does that differ?
Well, I would say surprisingly, I mean, surprising to me anyway. It used to be an answer I thought that only a few of us had experiences with, not just astronauts, but there's a number of different careers where by definition you are posted somewhere where you don't get access to other people when you want to. But now everywhere in the world, I think all of us understand that. and because of COVID-19. And I think what gets us through up on the space station, and we're actually quite lucky, is that the mission is just staring us right in the face. I mean, you look around, there is nobody else but the 6 of you. And if you don't get something done, or you don't enable your crewmates to get it done, or help them or support them, then then it's not going to get done. And it's so clear to us that the mission, we just know that the mission is more important than whether we wish life was different. And down on the ground, I think the mission is clear as well. It's just not, sometimes, I think focusing on it can really help, which is keeping each other safe, keeping our families safe, and doing everything that we can to advance humanity one more step. And each of us has a role. And I think COVID-19 actually has helped us realize that every single one of us has a role in that.
Another question on the same lines. So it's from one of our panelists who's in grad school right now, and she is studying stroke and the effects of microgravity on the brain. She asks, is something that clinicals as seen as eligible to study actually in space?
Well, I guess I'm not exactly sure what as clinical means, but one thing that limits our ability to study things in space is just the practicality of the numbers. And when someone tests a drug down here on the ground and says it's safe for you, it's tens of thousands of people have taken that drug. Or when someone makes a study and says, we've decided that maybe this is related to heart disease, there are so many data points, N is equal to so many. Thousands and thousands, if not millions, right? And then up in space, our numbers are more like N equal to 6. And it's kind of a microcosm of one of the things that we need to look at down here is to make sure that when we're studying what makes things safe for people, what are problems that people have, is that we actually study a broad population. And for example, if we don't study enough things about women, then we're not going to know whether it's safe for women. And when it really comes down to going to Mars, we won't know whether women can go. And so making sure that we are looking across populations, because women and minorities, we have some different health factors than are for, the sort of general white population. And so it's important. So I think our numbers are pretty low to be able to study stroke. But at the same time, it's something certainly that we should take advantage of the microgravity environment to study.
All right. Thank you so much, Katie. We're probably going to move on to the closing session. Also, we can still take some questions in the Q&A tab, so please feel free to ask them. Thank you so much, Katie. Once again, it's always wonderful to have you at CC. You're quite the celebrity, and for good reason. And closing in today's very successful Earth and Space Exploration Day is Rick Alling, who is becoming quite the celebrity himself. Take it away, Rick.
Well, thank you. And I didn't have to go to space to do it. No, I don't take credit for being the celebrity that Katie Coleman is. I was just reading, though, a day or two ago, and I just looked it up, that the first astronauts to go to the space station was 20 years ago at the end of this month. So we're kind of counting down to a 20-year anniversary of continuous human occupation in space, and Katie was part of that project in many ways, and so congratulations. And it's kind of different to think about sometimes that, while we're going around along our daily lives and all that stuff, there's people flying up over our heads, and they've been doing it now for 20 years. That's pretty amazing. I'm about to sort of close. My name is Rick Alling, and I'm the director of the Marston Exploration Theater. You see that in the background behind me, and I also point out that it's empty. We would be there right now today if we were on campus and if we were being able to meet and do that kind of thing. So I'm going to just kind of take and do some comments and tell you some of the ways you can engage with us virtually in the future. And I'm going to bring to close this 3.5-hour journey that we took on this morning and into the afternoon. And along the way, we learned that ASU School of Earth and Space Exploration is a multidisciplinary, modern research institution effectively organized to ask and explore the biggest questions in the universe. That's an important thing. Our school is organized to do that because of our size, because of the funding we get from NASA. We can attract the best faculty, and then that attracts the best researchers, that attracts the best students, and you can see how that just sort of that drives the project like it does. I like to think of our school as a 3-legged stool. we're a research institution. We talked about that. And along today, you were able to go into some of the labs and learn about the projects we're working on right now. We are a teaching institution. Indeed, students you met today are headed for undergraduate and graduate degrees in science and engineering. But we are also an institution. Number three is we are also an institution that takes very seriously our role in the community. This isn't just an add-on or a disposable activity for us. In fact, pre-pandemic, we had over 25,000 people visit our school every year on campus and do what we're doing today, learning about the institution and the research that we do. We think of our community as populated with lifelong learners, and visiting those facilities on campus, you can sort of engage with us in the most recent and current of research and institutional knowledge. We heard from over 50 presenters today, including our director, astronaut Katie Coleman. I'm always sort of charged up by her enthusiasm for her work. And we also met members of our faculty, research professors, doctoral and undergraduate degrees, and some outreach staff. I hope you have a sense of the size of the program, and it gives us the confidence to engage in these tough questions. But I also want to acknowledge that the effectiveness of the program is actually seen in the quality of our people. Certainly faculty and leadership and all of that is there, but no doubt you've also recognized the passion that our students have for their chosen fields. And it just makes me feel wonderful that they are engaging now, and they're going to take the collective body of knowledge that that we're learning about into the future. And so that's really one of the things that EC Day brings to you is it's a program that you have access to in your community, and it is full of students that can really charge us up to think about the future as being better than it is today, because they're there and they're interested. So you just participated in one of our virtual programs, and there are more. We didn't stop once the pandemic started. We just continue to engage. And so just coming up, I'm just going to give you some announcements of some things. You just met astronaut Katie Coleman. She will be back and available for a presentation. We call it Ask Me Anything with astronaut Katie Coleman. And that will be next Wednesday, October the 28th, and it's at 1 p.m. And so you're going to see in a couple minutes a slide on the screen as I kind of close out. We'll leave it up for a little while, and it will give you all kinds of different opportunities to find out about things and engage in us and sort of look up what we're doing and become involved in things. So that next Wednesday at 1. Wednesday evening, that same day, in the evening at 7, we're doing what we call the Virtual Night Sky. This is a program that I host, and we started this, oh gosh, back in June, end of May and June. And we've been doing this essentially every Wednesday evening ever since. And so this Wednesday evening, it just happens to be an ocean theme of all things. We're going to look at the night sky that's associated with the watery part of our celestial sphere, where fishes and water animals and those kinds of things happen to habitate. So we're going to look at that. And then we're also going to talk a little bit about the way Polynesians, ocean-going equatorial Polynesian cultures over the years, how they have looked at the night sky, which you'll sort of see some similarities and differences to the way that we do it. And we'll talk about that on Wednesday night. A couple Thursdays later, on November the 12th at 7 p.m., it's an ongoing science lecture series that we have. We usually engage in the Marston Theater, but it is going to be virtual. And so on Thursday, November the 12th at 7 p.m., Elizabeth Trembeth Reichart is, she's one of our newer professors. She's fascinating to talk to and learn about her work. She does most of her work at the bottoms of the oceans and studying sort of the chemical processes that happen down there and how life is engaged. And so she is actually designed a program, lecture for you called Life in Rocks. And you'll have to just learn what that means, right? What happens inside rocks and what happens to life at that kind of scale. So I need to sort of get some thank yous out for today. So Alicia Hyatt, Alex Blanche, Spruthi Kasharai, they were the student docents and were sort of like keeping everybody on track. And they're the ones that had to jump in and sort of like, sort of fix some things and do some things along the way, fielded some of your questions and introduced many of your presenters. And so they were frantically working in the background, keeping this thing moving and keeping it organized. I also would like to mention that myself and my colleague, Meg Hufford, Meg has been online all morning as well. She and I are essentially the team that manages the activity for the general public for the School of Earth and Space Exploration, especially those things that happen in our school and in our buildings and in around. And so Meg has been the sort of organizer and mastermind of the Earth and Space Exploration Day up until now, and that is in transition. And so let me also introduce and thank Kimberly Baptista. Kim set up this entire webinar, got this thing organized, got this schedule going, communicated with everybody how they had to be, where they needed to be, when, and that's a monumental activity. This is her first year taking that on, and I think she did an excellent job. So, so we thank Kim Baptista for doing that. You need to check your email for an upcoming survey. It will it gives you a chance to tell us about what worked and what doesn't work, and what you want to see, things that you'd like to see more of or engage in with us in the future. And that's the way to communicate to us. So we think we know what you want to hear. We present these programs, but we really know what you want to hear because you respond to surveys, and we sort of like, we take that very, very seriously. So thank you very, very much for joining us for this this amazing EC Day and this amazing year of differences and resilience and the way we sort of have to learn to communicate. I hope you've learned a lot along the way, but I hope, like me, you sort of think that, you know, as weird as things are in our world and as uncertain as sometimes we can sort of think things are going to be, there is a base of young people and researchers that are just working every single day in the background. And every single day, they're producing amazing science and moving that along and culturally moving that from generation to the next. And if you got that out of today's program, I think it was a tremendous success. So we will see you along the way. Thank you very much for participating. And I hope you join us for more School of Earth and Space Exploration activities going into the future. Thank you.